Hi everyone, welcome back. Today we're going to go over the asynchronous learning section for IV models. And so we're going to go over a data example from the Angus and Evans 1988 paper. In this paper, they're looking at female labor supply with having a third child as their IV. And so looking at female labor supply when a woman has children has been a widely studied paper and discussed at this point of time before this paper was published. And in the paper, they even touch on the Becker utility model on having an additional child and what that brings in terms of the family's utility. And they talk about the idea of offsetting the cost of additional children by either the husbands or the dads working more, or the women, if they're unable to hire daycare, to work less. They also talk about the impacts of having children on different income levels and socioeconomic status. And they discuss that later on in the conclusion as well. But let's just go over some specifics. So in this paper, they're gathering data from PUMS and a variety of other sources as well. And they have data from 1990 and they have data from 1980. And they have data from different age cohorts. Primarily in this paper, they focus on the cohort 21 to 35 years old because the women in this cohort are believed to need to take care of their children because their children are young enough to still need that care and supervision, the first and second child, while older cohorts are believed to not have as much of an impact on female labor supply because maybe their first child is older enough to take care of the other children, or themselves at least. And so that's one of their reasons to only focus on this cohort. And now we're just going to go ahead and take a look at the OLS regressions that they use. And they use those to discuss the different correlations that have been made prior in other literature prior to this. And then they introduce the IV regression, which is able to help draw a causal relationship between having that third child and female labor supply. And just to note here, the reason why they're able to argue that this is an IV that's correlated to, our endogenous variable but unrelated to the unobservable is because having the different sex of children, or the different genders of children, is random variation due to biology. And so they're able to argue that people who have two children of the same sex are more likely to have a third child because they are motivated to have, a child of every sex. Whereas individuals that have two children of two different sexes are maybe less likely to have that third child, but the gender or sex of the child that a person has is random variation. So they're able to leverage or use this random variation as an exogeneity that's determined purely random in order to deal with the endogeneity problem of looking at female labor supply that people have struggled with in past papers. That's the motivation here. So to start off this example, we're just going to clear out any data sets that may be loaded. And now that we've set our working directory, we can load in our data set. Okay, so now that we've loaded in our data set, it's always a good idea to take a look at what we're working with. So these are our variables, and we have kid count, which is the number of kids a person has had. More kids is equal to 1 if mom had more than 2 kids. So this one we're going to see is a dichotomous indicator variable. So it's going to be 0, 1 coded. Boy first is equal to 1 if the first kid was a boy. Boy second is equal to 1 if second kid was a boy. Same sex equal to 1 if first two kids have the same sex. Multi-second is equal to 1 if second and third kids are twins. So another thing that they look at in this paper is having twins, because that's also random variation, and they focus on the idea of having twins on the expectations of the different sex of the twins and what that's going to have as an impact on female labor supply as well. Then you have age of the mom at census, mom's age when she first gave birth, and then your demographics. Did mom work for pay? Mom's week worked, hours of work per week, labor income per week, and these are other dependent variables that are looked at and investigated later on in the paper in the concluding tables. So that's what we have to work with. And now we're going to define our log for our variable. So now we've opened our log file. So in our last example, I didn't go over how one would open a log file, but it's very important to have that and turn that in when you are turning in problem sets. So what I do for my log file is I won't run the log file or open it until I know all my code runs well. You could open the log file when you start your problem set, even though you know your code won't run well, but an easy way to do it is to code everything out. Run your do file by pressing this do button without highlighting anything. It'll run the entire file. And if no error message comes, you know that the whole file runs. So you could always open the log file, run the entire do file, close the log file, and then you're just showing us that all your commands run. Because if suppose you've named a file something different from what we have on our machine or something like that, there may be issues in us running your files. So it's always a very good idea to open your log file. And by doing the using pums 80, we're just naming it. So now it's created a log file named pums 80. So now we're going to generate some new variables. So let's generate 2 boys is equal to boy first times, or interact with boy second. So we're basically saying let's create a variable generated by the interaction of 2 dummy variables that's equal to if the first variable boy first is equal to 1 if the first boy, or if the first child was a boy, and then this boy second is if the second child was a boy. And if the first and second child was a boy, then that means that the couple here had 2 boys. And so we're going to create another dummy variable based on that. And so it's only going to equal to 1 when the boy, let me go ahead and actually change the order here so that we can see everything together. So it's only going to be 1 when boy first and second are both a 1, because they're multiplying this and this. So 1 times 0, give us a 0 here. Okay. So now that we've done that, let's create another one. Let's generate when 2 girls equals 1 minus boy first times 1 minus boy second. So let's go ahead and run this, and we can also take a look at this. So 2 girls will only equal a 1 when these are both 0. So why is that the case? Why did we use 1 minus boy first? It was because boy first is only a 1 when the first child was a boy. So for it to be a girl, 1 minus boy first would be 0, meaning it's a girl. So we want both of these indicators to be a 0 because the way it's coded is that 1 would be the first child as a boy, 0 would be first child as a girl. So that's why we use this 1 minus. So here we look at the summary statistics of our data. And if you have the paper open, we're looking to table 2 descriptive statistics specifically. And we're looking at the 1980 and this column here. And we recreated that pretty closely. So kids count 2.5. Here it has 2.5, children ever born. And then we have 2 girls, 0.24. And 2 girls, 0.239, they're more exact. 2 boys, 0.266. 2 boys, 0.266. So we've just recreated that third column when we run the sum command because we're looking at the 1980s data in this data set. So after we're done doing our descriptive statistics to recreate table 2, column 2, let's go ahead and run a correlation between our variable more kids and our variable same sex. And remember, more kids is a dummy variable, so it's going to be coded 0, 1. So 0 means the person in the data didn't have more than 2 kids, and 1 would mean that they did have more than 2 kids. Whereas same sex is in reference to if the first 2 kids are the same sex. And so when we're running this correlation, we want to think about our DAG, our directed acyclical graph. And if you guys have been following along with Scott Cunningham's causal inference mixtape, which I highly recommend, you'll remember that when we have an endogenous relationship like we do with our dependent variable, female labor supply, and her childbearing, in the paper as well as in the textbook, it's mentioned that there's many correlational studies that have been done between the amount of children a woman has had and, female labor supply. But because the relationship is endogenous, there isn't any causal claims that can be made. And so by being able to leverage the same sex as an instrument, as well as twins later on, we're going to discuss, we can draw out some causal relationship between fertility, specifically having more than 2 children, and female labor supply. So going back to the DAG, if we think about Y, our dependent variable is female labor supply, and just to stick with the notation from the textbook, D would be, in this case, more kids. That's the relationship that's typically studied. Z, our instrument here, would be same sex. And so the correlation should be that the endogenous variable should be correlated with our instrument. And the only way in which our instrument is correlated with the dependent variable is through this endogenous variable. And so we can go ahead and run this correlation. And we can see here our correlation is 0.0695. And so it's always important to run this and, really think hard on what our DAG is and how our relationship is running from our instrument to our right-hand side variables, and then leading to our endogenous relationship with our dependent variable. And now that we've taken a look at this, let's go ahead and do a regression looking at whether the mom worked or not, so 0, 1 again, based on if she had more than 2 kids. And this is the typical regression that's been studied in previous papers. And we know from previous papers there's a negative relationship. A mom who has more than 2 kids compared to a mom that doesn't have more than 2 kids, is going to work less on average by negative 0.11, or if we want to make it a percentage, 11.5%. And the problem with this model, though, is that there's an endogenous relationship between the mom working and having more kids. There's other factors involved that's not allowing for a true causal relationship that are also part of the error term. There's another example explaining more about how unobservables in the error term that could be correlated with some of your right hand side variables causing endogeneity issues. There's some more explanation of that in the mixtape, and I suggest that you take a look over that, where Scott Cunningham discusses school and ability, and that's a really good explanation to better understand where these endogenous relationships lie in terms of the econometric math behind it. So now that we've done this OLS bivariate regression, let's go ahead and start actually doing our IV regression. And this is the same as our Wald estimate. And if we want to use the same notation from class as well as our DAG, we have the variables y, x, z, and w. So the syntax for our IV regress is going to look like this. We're going to have IV regress to SLS, so we're telling Stata it's going to be two-stage least squares. Y are dependent, W, and then X equals Z. And W is just our other exogenous variables that may be included in the model. X is going to be our endogenous variable that we're instrumenting for, and Z is going to be our instrument. And in this case, we're going to have W being null, Y equals worked, X equals more kids, and Z equals same sex. And now we can run this framework. Okay, let's see what happens. If this command doesn't run for you, you may have to do ssc install IV regress. I think it's IV reg 2. If I'm not mistaken, let's check it out. Actually, I take that back. That's a different way of running IV regress. Should be ssc install IV regress if you don't already have this command available. And so it gives our two-stage least square, and it does it all in one step. So if you're reading the notes or the book, they talk about first doing your first stage, and then after doing your first stage, then you go ahead and you look at your reduced form and your second stage. Whereas here it's just doing everything all in one step. When you are writing a paper, you are going to want to do the first stage. That way you can report the F statistic and show that it's greater than 10. So you've helped satisfy your relevance assumption. But that's not what we're doing here. And if we just take a second and pay attention to this coefficient, it's also negative. It's actually more negative than this coefficient is. But if you notice, the standard errors are quite larger. It's 0.029 as opposed to 0.002. And Scott Cunningham does discuss this in the mixtape. It's typical to have larger standard errors for our IV. So, it's not the case here. It's still significant, but it is the case where they don't end up being statistically significant, or there are some issues because of these standard errors, so that's something to note as well. And now we can go ahead and look at something that's a little bit interesting with our standard errors. Let's say we want to take the proportion. Let's say we do display 0.002, 0.246 divided by 0.029, 1242. We actually get 0.0695, and if we remember back here, our correlation was 0.0695. So the interesting thing to note here is that the proportion of our OLS regression of our endogenous relationship divided by the standard error from our IV regression actually gives us the correlation between our instrument and our endogenous variable. So that's something interesting to note here. And now let's go ahead and recreate some of the first stage estimates. And these are located in table 6, columns 4 through 6. Okay, so now let's take a look at our first stage estimates. So we want to look at the married woman sample, and this is going to be in table 6. This one. And it's going to be columns 4 through 6 that we're looking at for married women. So let's run our normal OLS regression of more kids and same sex. And we're actually going to be replicating column 4 here. So these are the OLS estimates of more than 2 children equations. For the same sex, we get 0.067 as our coefficient, and they get 0.0675. Standard error of 0.0019, and we get the same standard error of 0.0019. So this is just looking at our naive regression of what has been looked at prior, correlations of how does having the same sex children, how is that correlated to whether one has more kids or not? And we see, using our naive regression, that there's a 0.067 correlation, which is exactly what we found when we, pretty close to what we found when we did our correlation of more kids and same sex. So now let's go ahead and replicate column 5 here. So here, the difference is that they've added boy being the first kid, boy being the second kid. They also have same sex, and they have other variables as well, such as the age of the female and the demographics. So let's go ahead and add those. If we don't remember the meaning of some of these variables, we can check here. So age M1 is age of mom at the census, and age FSTM is mom's age when she first gave birth. So let's do this regression. So this regression is specifically replicating column 5. And this one was replicating column 4. And we're looking at table 6, columns 4 through 6. Okay, so now we can take a look at these results and we can compare it to the ones that they found in the paper. So this is column 5 that we're replicating. And so they look at boy first, boy second, and they say that for married women having more than 2 kids, right? When the first child that they have is a boy, there's a negative correlation, holding all else constant, with the woman having more than 2 kids. And then the same thing for the second, there's a negative correlation with having more than 2 kids if the second child is a boy. But there's a positive relationship if there's the same sex for the first two children. And see, they list here with other covariates, yes, and so that's why we've added these other demographics and age variables, and we get these same results here. So now that we've learned how to replicate a couple columns, let's go ahead and replicate one more here, column 6. So the difference is that they look at the first child being a boy, they look at having 2 boys, 2 girls, and they also look at the covariates, but they don't look at the second child being a boy or the same sex. These are the same covariates that we had last time. The only difference is that our variables of interest have changed a little bit. Now we have 2 boys, 2 girls instead of having this whole list. And we can run this regression. We get positive coefficients for 2 boys, 2 girls, negative coefficient for boy first, which is the same as what we had here. We had a negative coefficient, but the magnitude is smaller here. We have 0.0015 as opposed to 0.011. So basically here we're saying that the relationship between having more kids, more than 2 kids, if you have 2 boys, there's a positive relationship holding all else constant. If you have 2 girls, there's a positive relationship. But if your first child is a boy, there's a negative relationship. And so here it's saying, this is another way to kind of decompose same sex. They're saying that if you have 2 boys, there's a positive relationship of wanting to have that third child so that you have a girl. And the same with if you have 2 girls to have a boy. Okay. So this test that we're running for this regression that we're running for column 6 is just to compare with this column 6, and we get the same results. Provide those results. Let's go ahead and run some tests on the coefficients. So in this paper, they're going to be using same sex as an instrumental variable, but they'll also be using the 2 boys, 2 girls separately as instruments. And one important thing when we're looking at these 2 coefficients, first we want to understand 2 boys is equal to 1 if the mother has 2 boys, or 2 girls is going to be equal to 1 if the mother has 2 girls. And same sex is basically composed of these 2 variables. And so one thing we want to make sure when we're running this regression is to see whether they're both adding some kind of significance or meaning to our model. And we can refer back to our last econometrics class when we used to run f-tests for coefficients or betas to see whether they're useful in the model. And we're going to go ahead and run a couple of those right now. So let's go ahead and test first whether the 2 boys coefficient is statistically the same, so no different than the 2 girls coefficient. So we can do that using the test command. And the way that this hypothesis test works is that it writes 2 boys minus 2 girls equals 0, meaning if you add the 2 girls to the other side, they're equal to one another. And since it's statistically significant, we can reject the null And the null hypothesis here is that they are the same, the coefficients are the same, so they are actually different. And then we can run a secondary test, f-test, for each individual coefficient. So here we're just going to write them side by side rather than with the equal sign. And this is to test whether each individual coefficient adds to the model, gives some significant meaning. And in other words, in terms of statistics, we're testing whether 2 boys is equal to 0 or not. Is 2 girls' coefficient, the same as equal to 0, or does it actually hold some statistical significance? And again, we reject the null hypothesis. The probability is, much lower than 0.05. We rejected it at the 1%, 5%, and 10% level. So these coefficients are meaningful to the model. So that's just something to go ahead and look at in this case. And now we're going to go ahead and store residuals that we're going to look at later on. This is going to be in order to help us check for over-identification, but we'll discuss more later on. When you run a regression, if you want to store the residuals, you do predict. You put the name of what you want the thing you're predicting to be. So let's just do residuals from the first stage that we just ran. And this is when we have 2 z's, or 2 instruments. And then you have to put this comma re. That's what Stata reads in as residuals. So it's the predict command with a subcommand comma re. And I'd already ran this, so let's drop this residual and remake it. Perfect. So now it's stored the residuals for us. So now after we've stored those residuals, let's go ahead and run our first stage regression for an exactly identified model, meaning that we're not going to put in many instruments, just one instrument. So let's go ahead and look at this regression. So this is first stage for exactly identified model. And this is our instrument, same sex, and our dependent variables, more kids. Now we can take a look at our reduced form. And the dependent variable here is whether the mom worked or not. And we're going to use the instrument. And we want to pay attention to the t statistic on the same-sex variable. And we're going to want to compare this later on to our 2-stage least squared t statistic. So let's go ahead and now look at, now that we've done first stage in reduced form for one of these models here for married women, let's move from the OLS to the IV regressions in table 7. So this has the OLS and the 2SLS. And so we're going to want to focus on columns 4 through 6 again in the middle. And here we have different dependent variables: worked for pay, weeks worked, hours per week. So let's go ahead and start with the OLS for worked for pay model. So we're basically running the same exact regression, we're just changing our dependent variable here. And if we're going to compare the results, we get a negative 0.166 coefficient for more kids. And here we get the same thing. They've just rounded to the third decimal. And so we can see that when our dependent variable is worked for pay, having more kids, more than 2 kids, there's a negative relationship between having more than 2 kids and having a mom work for pay. And here we don't have our instrument. We're just looking at the OLS. Let's go ahead and look at our two-stage least squares work for pay model using IV regress. So we're going to have IV regress, 2SLS, worked, whether the boy was the first kid, boy was the second kid, age of the mom during census, age of the mom during the first kid, and then other race demographics. And now we're going to add our endogenous variable as well as our instrument. So more kids is the endogenous variable we're correcting for by instrumenting using same sex. And so let's go ahead and run this regression. And now we've actually looked at this 2SLS. That's what we're using, and we're using same sex as the instrument. We get negative 0.12. So we're still getting a negative coefficient, but the magnitude is slightly larger here. We can run the same model using our 2 instruments that we tested earlier that were significant. We found that 2 boys is not equal to 2 girls. There are different coefficients, and we also found that 2 boys is significant to the model and 2 girls is significant as well, so we can run them as 2 separate instruments instead of composing them all into the same sex variable. So let's go ahead and run that model as well. To recreate this column here, the 2-stage least squares with the 2 instruments, 2 boys, 2 girls. So we can do IV regress, 2-stage least squares, and we have worked for pay as a dependent variable, whether the first child was a boy, age of mom during census, age of mom during first birth, demographics. And an interesting thing to note here is when we're doing the more kids equal, we can do 2 boys, 2 girls, right? But we can also add in all the other exogenous variables from our list, and we're going to get the same results. And I'll explain that right now. So when we run this model, it shows our instrumented variables more kids, and our instruments are all of our exogenous variables. A better understanding of why all of our exogenous variables are showing as instruments, we can look at the syntax for IV regress. It shows that variable list 1 is a list of exogenous variables, variable list 2 is our endogenous variables, and then variable list IV is a list of exogenous variables used with variable list 1 as instruments for variable list 2. So basically, based on the syntax, this command IV regress is checking each of the exogenous variables as instruments. And so for this regression that we just did, IV regress 2SLS, when we do more kids equal same sex, it was also checking all the other exogenous variables. So we can actually write, when we're doing the second instrument to replicate this 2 boys, 2 girls, we can write it as more kids equals 2 boys, 2 girls, and all the other exogenous variables. It's going to give us the exact same results because the way the syntax works, it is going to test all of the exogenous variables. So if we run this one, we're replicating this column here. We get that negative 0.113 coefficient here. And our standard is 0.027, which is what we get here. And just to compare with the OLS, we have the magnitude being slightly smaller for our work for pay based on having 2 boys, 2 girls, and the relationship with whether the mom worked for pay. It's very slightly smaller, but our standard error is a lot larger though. So that's something to take account of. And we can actually show a different kind of way of running IV regress. We can use a different command. It's called ivreg2. If you don't already have it installed on your machine, you can do ssc install ivreg2. This is just another way of running an IV regression, and it's just another built-in function on Stata. There's just a few things that are slightly different. You have more kids equals same sex. You have boy first, boy second. Age, a female during her first birth. Black, Hispanic, other race. And you can actually use, you can either run it like this, or you can use a partial command. So let's first run it like this. And so the difference here is our exogenous variables go to the end, and you have instrumented for more kids, and your included instruments are these, and your excluded instrument is same sex. And we can take a look at our output here. So we get negative 0.129. Which is also very similar to what we have here, but slightly different. We get negative 0.120 here. And we can also use the partial command. So let's do help ivreg2 to learn more about the notation. So you have your dependent variable, your variable list 1, variable list 2 equals the IV, so your endogenous equals the IV. And if we take a look here, there is a subcommand for doing partial here. So we can look at this. So here it talks about partial. So the partial option is most useful when using cluster. So your exogenous regressors plus the excluded instruments. In these circumstances, the covariance matrix of orthogonality conditions S is not a full rank, and efficient GMM and over-identification tests are infeasible since the optimal weighting is this. So the problem can be addressed by using partial to partial out enough exogenous regressors for S to have full rank. So the similar problem arises when the regressors include a variable that is a singleton dummy. So with a 1 and n-1 zeros or vice versa. So let's go ahead and try running the same regression, but let's actually use a partial command. And let's put in, like it had mentioned, our other exogenous variables. Let's see what happens now. And I didn't add age M1, so let's go ahead and do that. And so now we get negative 0.120, which is the exact same estimate that we get here when we run it using IV regress two-stage least squares. So this is just another way of running it, and it tells us that we partialed out all of these. It also gives us our Sargan statistic for over-identification and our weak identification and under-identification test. So when we run these kinds of models, we want to make sure that we're not over-identifying the model, meaning we're not using too many instruments. And remember, there's no way to check if your first instrument you use is valid. You can only support this with a theory, underlying theory, or a belief that you have based on the way institutional knowledge, the way the data is constructed of why your instrument is valid, but there's no actual test. There are tests though in Stata that can look at whether an additional instrument is useful, because it's basically telling whether the additional instrument is useful for your model and giving us additional information, but it's using the assumption that the first instrument implemented is useful. So there's no actual test to see whether the first instrument is valid. And so let's just look at testing over identification. So we ran this model using IVReg2. Why don't we stick back to IVRegress with the two-stage least squares? And let's look at the work for pay model again, and let's look at when there's 2 boys, 2 girls, which we can actually just copy from up here. Let's go ahead and copy and paste this. And let's go ahead and also store the residuals from this model as well, like we did prior. And this is going to help us test for over-identification. So let's rerun this model, and then let's store these residuals, naming it whatever you'd like. And let's use the built-in Stata function of estat over id. So estat means it's a post command, post estimation, and over id just stands for over identification. And when you have a significant result here, it's basically saying that there is a potential for one of your instruments or your additional instrument to not be valid, but it's not saying 100%, that that additional instrument is not valid. You can look at help over ID to learn more about how Stata explains it. If you go here and you go to estat over ID, it explains that a statistically significant test statistic always indicates that the instrument may not be valid, but it's not saying that necessarily it's not valid. So that's good to know. And now we can try running the over-identification manually. So let's go ahead and do that. Now we're going to run our over-identification through brute force in a regression. And this is why we stored our residuals from our IV model. So we're going to run a regression using the residuals as our dependent variable. So 2SLS work for pay, and then we're going to use both our instruments as well as our exogenous variables as the regressors in this model. And our goal is to know that we have not over-identified, and to satisfy the Sargan test, we should not see that our instruments are related to the residuals. There shouldn't be a relationship between the coefficients of our instruments to our residuals from our IV model. Then we know that we haven't over-identified. And if we look at the magnitude of these coefficients, they're very, very small, all of them. And so because they're so small in magnitude, we can tell by brute force that we haven't over-identified our model, and we satisfy the Sargan test of over-identification when we use these two instruments, 2 boys and 2 girls. So after we run this over-identification by brute force, let's go ahead and run a different test for endogeneity. Let's run the Hausman test of endogeneity in the 2 instrument case. So we're going to still focus on when there's 2 boy, 2 girl instruments. And if you think back to the first time we stored our residuals, it was for when we had ran the first stage regression. And so we're going to now use that. So we're going to add the residual from our first stage regression to OLS of the structural model. And that's going to look like regression, and our worked is going to be our dependent, more kids, boy first, age, and then we're going to add the residuals as well. For the two instruments, we're going to run this. And if we notice here that OLS of this model actually generates the two-stage least squares estimates of the other variables in the model. So when we look at more kids, boy first, age, these are similar to the regression results that we see in the paper. And basically what we're showing here is that when we're adding the residuals from our first stage, when our dependent variable was more kids, which is our endogenous variable, and we're using our instruments as well as exogenous variables as our regressors, the residuals from there, when added to this model, provide us the same two-stage least squares results. And so we are ensuring that there was an endogeneity problem, but with the use of our instruments and our residuals from our first stage, we're able to show that there is an endogeneity problem that we've corrected for using our instruments. And so yeah, that you can read more is considered the Hausman test. And you can compare these results here, these coefficients, to the paper, and you can notice that these coefficients are the same as the two-stage least squares results. Go ahead and take a look at some of the other models that they've considered here. They have a dependent variable looking at weeks worked. And so let's see if we can recreate some of these regressions here for weeks worked. So we're going to use regression for our OLS one. Weeks, M1 is weeks worked. More kids. Boy. Okay, so let's see if we're able to recreate this, okay? So when our dependent variable is weeks worked, here we get a coefficient of more kids, and it's pretty high. It's in magnitude. It's negative 8.0449. So it's basically saying that a mother who has more than 2 kids compared to a mother who doesn't have more than 2 kids. Remember, because when more kids equals 0, that means she didn't have more than 2 kids. You know, the amount of weeks works decreases by negative 8.04495. So the relationship between how many weeks work the mom does and if she has more than 2 kids is very negative. So she's not going to be able to work as many weeks as compared to a mother with less than 2 kids, which is what we would traditionally think. And then we see these other coefficients that we've added, the controls, the boy first, boy second, how that attributes to the model. And if we compare it to these results, they get the same thing, negative 8.05 and a standard error of 0.09. And we get the same thing here. So let's go ahead and run our two-stage least squares model for weeks worked. And let's start with using same sex as the instrument. And that's this one here. We're doing column 5, row 2 for the dependent variable. And let's do regression. We're going to use weeks. Sorry, not this one. We just ran this one. We are going to do IV regression, weeks, And we're going to use boy first, age M1. And we're going to put more kids, our endogenous variable, and our instrument is going to be 2 boys, 2 girls. And what I'm actually going to do is I'm going to show you that you can actually put these 2 slashes here if you want to extend your code to the second line so that it's not going off the page. I don't typically do this, but you should do this if you want to be able to see your code all in one window. But you would have to put these 2 dashes before you open up these parentheses for it to work. So you have more kids equals 2 boys, 2 girls. And remember we talked about how we can just put in all of our exogenous variables because Stata is going to test all of them. Age M1, age FS, TM, Black, Hispanic, other race. Let's go ahead and run this regression. And I'm missing something. Okay, so you need to have 3 slashes here for it to work. And so they use the instrumental variable. We instrumented 4, more kids are endogenous, and then our instruments are all of these exogenous variables as well as our 2 instruments. And we were actually using same sex as our instrument here. Let's rerun that. Okay, here we are, and we get a coefficient of -5.46. And they get something pretty similar. It's -5.4. Let's see if we can recreate it closer. If I add boy second here, how does that change it? And now we get a coefficient of -5.40. So that's exactly the same. So when you add or drop some of the covariates, it is going to have an impact on your coefficients and your regression results. So the covariates do have an attribution to our main coefficient of interest. And so here we're finding the same results as before with the naive OLS. We still find a negative result, but we get lower magnitude, -5.4. And if we want to think about why that's the case, well, it's basically showing that we still have a negative relationship when we're looking at it in a causal framework, that the amount of weeks worked is still, or that having more than 2 kids compared to a mom with less than 2 kids is still negatively correlated with the amount of weeks the mom works. But by it being less in magnitude, we're basically saying that there could be other factors attributing to it, and that way it's not naively just attributing the 2 at such a high magnitude. And if we pay attention to the coefficients, this is about the same as this one. This is 1.25 here. This one changed signs. No, I take that back. Sorry, this is boy first. There was no boy second. And there was no boy second there as well. So that wasn't in the models, but age M1, let's look at that. That's different. So basically, adding this boy second added some value in the sense that it's taken up some of the variation or some of the results here and soaked it up, potentially. And so other than that, they all look pretty similar, and we're basically just showing that having more than 2 kids is still negatively correlated with the amount of weeks worked, but not to such a high magnitude. And now we can try the 2-stage least squares model with the 2 instrument case. So we're just gonna copy and paste this, and we're gonna run what I had originally ran. I had ran it with 2 boys, 2 girls. Let's rerun that one. And I'm going to take this covariate out because they don't use that in this model. try running this one. And they get negative 5.16. And here we're getting negative 5.16. They get a standard error of 1.2. We get a standard of 1.2. So I guess one thing to note again is that when we ran our OLS regression, our standard error was 0.089. It's gone up, considerably, which is something that's going to happen with the instruments. So that's something to realize. But we're finding pretty similar results. They're still negative. We don't have a sign change or anything like that. And it's still pretty large. It's just not as large as the -8. It's -5 instead. But yeah, so now we can just do another test for over-identification, just to remember how we do that. So we can predict residuals. This is going to be 2 SLS, and let's put it with weeks, because now that's the new dependent variable, comma res. And remember, this is just naming the variable. This is the actual command, predict and res, the two things in pink. And so we've stored those residuals, and now let's do it by brute force. Let's take the regression of the residuals from the instrumented regression, and then let's take the instruments and see what happens. So let's do this regression. And we find, so first, none of these are statistically significant. So none of them, statistically significantly explain the residuals, which is what we want. And none of them are very highly correlated based on the coefficients and the magnitude. We don't want, there to be a relationship between our residuals from our IV regression with our instruments. We don't want there to be a correlation there, and we don't see that. So we're doing good with the over-identification. And now if you still had your log open, I don't think I do at this point because I've been running this code for a while now. I guess I did. And we can close our log by just pressing log close. And that's everything I have for you guys today for IV regressions. Please feel free to reach out if any of this didn't make sense, or you guys feel like you need some more explanation on any of it, and we can go through it together. I would definitely, mark your questions down for the TA sessions. That would be a perfect place to answer them. And yeah, guys, good luck with everything. Talk to you soon.